Okay, so we're looking at daily quiz number 2 coming your way to coming to class tomorrow. Yeah, 5 minutes. Quiz maximum time, 5 minutes. Hopefully, the 3 problems I'm going to put up here might take you a minute and a half in December. All right, so we're going to solve this equation. There's a couple of different ways. There's completing the square, there's quadratic formula, but there's also factoring, and that's what you would do here. So hopefully we look at this from a conceptual standpoint. Rectangle, and what we're really trying to do is get an area of 0, which means we're either going to cancel the length or we're going to cancel the width. But in order to do that, we have a length times width equaling 0 format. Trinomials. Today's quiz, you had a chance to factor 5 problems, and it's still going on. The only difference is one more step, and you're done. All right, so I'm hoping that you start to think of combinations, factors of 30 that are 7 apart. Hoping 3 and 10 pops into your head fairly quickly. And you are, remember, hitting that space bar on each of these problems. And I want a minus to dictate. So therefore, the bigger magnitude value gets the negative, gets the positive, and then we have ourselves our length, x plus 3. What cancels the length? You cancel the length, it's like squeezing it, top to bottom and side to side. Area disappears. Hopefully you can see that. If I make the width 0, and the width we'll call x minus 10, what makes that 0? An x value of 10, which means that I would have 10 plus 3 times 10 minus 10. And if I'm not mistaken, 10 minus 10 is 0, and 0 times anything is 0. So that's one of the answers, and the other one obviously is -3 if you're following that discussion. So there's problem 1. All right, problem 2. And we just started looking at different situations, factoring situations. And the first rule of factoring is take out what's common, but I'm not going to give you that situation here. Just going to get you practice with coefficients of 1 at the moment. Well, no, I think we did. I think I've got to give you a coefficient of 2. 2 of these maybe. But let's go with x squared plus 4x, and let's do 12. So let's go -12. All right, let's set that to 0. So I'll just keep going. You pause the space bar. X plus 6 times x minus 2 equals 0. And so answers of -6 and +2. And those are the roots. Sometimes, intersecting 0 are x-intercepts on a quadratic. So that's what you just found. The x-intercepts, -6, +2. Obviously, what's between these? Add them up, -4 divided by 2. -2 is the number that's in between these. And I think we can always see a kind of a square process. -2 plus 6 is 4. This is usually -4. -2 minus 2. Talk about that relationship later. N minus b over 2a is another way to get that. All right, so that's the second one. Let's do another one. All right, let's try x squared. How about we try -8x, and let's try +16. Equals 0, of course. All right, so 2 numbers that multiply out to be 16 and add up to -8, -4, and -4. The product is positive. Adding up those 2 terms gets us x plus 4 squared. I'm sorry, -4. X minus 4 squared equals 0, and we're trying to get better at binomial squaring as well. Double that product. Square the last term. I hope you can see that quickly and easily now. So this is called the double root, because we really have x minus 4 times x minus 4. All right, and really just parabola over here at +4. Okay. So that's the only answer is 4. We call it a double root, so that was the third one. All right, let's get a coefficient of something other than 1, so we can make something up over here. Let's put 1, all right, so let's go with 2x squared minus 3x plus minus 5 equals 0. Okay, you hit the space bar. Oh, what do I know? I know I got a 2x and an x, and that has to equal 0. I know that if I pick a 1 or a 5, well, that number is really doubled. I really get the number 2 and the number 5. So there's a 1, there's a 5, but it really is turning into the number 2, or 5 times 2, 10. Now, what goes with a 1? A 5. Is there a way to make a 2 and a 5? Oh, 3. Yeah, I can do that. All right, so I am going to do, I want the 5 here. No. And the, oh, because I'm using a 1. There we go. So there's 2, there's 5, 3 apart. I want it to be negative. So I want that one negative. I want this one positive. We've been working hard to answer these questions quickly and easily. I hope you look at that and you go, oh, x equals 5/2. 2 inverse operations. The inverse is subtraction, addition, and the inverse of multiplication, division. Okay, so if I saw 4x minus 7, what makes that 0? 7/4. Okay, so keep an eye out for that. I'll do one more. This time I'll beef it up a little bit. Let's look at 2x squared minus 2x minus 12 equals 0. Well, the first rule of factoring is take out what's common. So 2 times x squared minus x minus 6 equals 0. You could do that, or you could notice that everything is even and just divide everything by 2. X squared minus x minus 6 equals 0. 2 numbers that multiply out to be 6 and then they're 1 apart. So x minus 3, x plus 2, because I want the negative to win. So 2 answers. One of them is 3, and the other is -2. And you're going to have one of those questions come your way tomorrow. Okay. So there's all kinds of factoring practice on the internet. Feel free to open up a web page that gives you some practice with the answers. It's a skill you got to have. Now we're going to remember the square roots, what they are. Side of a square. What's the smallest a square root can be? Well, I can make smaller squares. And you're getting a sensible limit right now, whether you know it or not. So I can get that down to 0. So the square root of 0 is most important. That's what kicks off. And then everything else gets bigger, unless I put a minus sign in front of it, then everything gets smaller. All right, so keep in mind, critical. All right, and what happens when I put a 0 in? I get a 0 out. What happens when I put a 1 in? I get a 1 out. What happens when I put a 4 in? I get a 2 out. Altitudes are increasing, but not as quickly as the area it takes. So that's why there's slow increase here. All right, so let's have at it. 5 problems. Okay, so let's put a 5 and a 7 there. And let's put a, I don't know, how about an 11 and a 19? All right, so we have a 5 and an 11. And we want the 5 to act like a 0. So we got x minus 5. When I put an 11 in here, I get the square root of 6. That's probably not going to work for this problem. So let's put a 5 in. That's over here. So drop it in, you get a 0, you want a 7. Hoping everybody's got that down right now. This is the square root change. But I want to get from 7 to 19, which is square root of 12. Okay, so there's ways that I could simplify this, but I'm not going to talk about that at the moment. So hopefully you would put a 6 here, and you can see the change, the operational change that is occurring. Let's try another one. Let's look at, and I'll give you a challenge question at the end here. Let's look at 4. Let's go -4, 7. Let's go down in this direction. Let's go 18. Something smaller than 7. How about we go 2? All right. Square root of x plus 4. When I drop a negative 4 in, I get the square root of 0, which is the smallest square root possible. I put an 18 in, and I get the square root of 22. That's going to come into play. Right now, I want a negative 4 to get me a 7. That's done. And now I want an 18 to get me 2. Well, there's only one way to get to 2 from 7. That's to go down 5. So whatever is produced operationally here, I got to get rid of it. So if I put 18 in right now, I have minus 5 times the square root of 22 plus 7. Does that equal 2? No. That number in my way. It's not anymore. Remember, the square root of 22 over here is the same thing as putting it there. We talked about the different ways you can multiply a number times a fraction. It's 3 different ways to do it. Seeing it this way is what you're trying to see. All right. So that's 2. Here's the third one. Let's try 3, get you negative 8. And how about we go 0 gets you 9. You're still trying this on your own. Well, I see the signature square root, right? Maybe I should have done that at the beginning. What are the nice numbers? 1, that's 1 unit, 4 might be here. If that's 4 units, 9 might be here. What's the square root of 0? 0. What's the square root of 1? 1. What's the square root of 4? 2. What's the square root of 9? 3. Hopefully you can see that slow growth. All right, so we have some growth here. I want 3 to act like a 0, kick this thing off. So x minus 3 makes the square root of 0, minus 8. How do I get from minus 8 to 9? I got to go up 17. What do I get when I put a 0 in here? I got a problem. That can't work. Okay, so let's make that 8, 9. Let's make it 9. All right. Oh, I hate the same numbers anywhere when you first learn. Let's make it a 10. All right, so what do you get when you put a 10 in here? Most people are just saying you get 7 units. You get 7 units of linear change, but it's inside an operation. So numerically, when you drop a 10, you get the square root of 7. That's what's going on numerically. And we got to make the numbers work. All right, one more. One more. And then I'll give you the challenge. I'm not going to answer the challenge. I'm going to leave it as a challenge. But right now, let's talk about y equals. Let's start here. Let's go down. Let's look at 1120. And let's go over here to 1950. Get you, I don't know, 1. So what have I got? 1120, x minus 11 plus 20. I put 1950 in. I get the square root of 1939. Very good year. Except it was the start of World War II, so I take that back. Okay, and 1 is less than 20. How much less? Gotta go down 19. You put that equation into a graphing calculator or Desmos, some graphing program on the internet. You're going to get that, provided you know how to work with domain and range. And the domain is x's have to be greater than or equal to 11. Nothing over here. And the range, the y values, they're all less than or equal to 20. Okay, so I'm talking domain and range a little bit. Here's your challenge question. You are not allowed to answer it with any kind of number in here with a minus sign. Well, I'm misleading you right now, so I got to be careful what I say. All right, I do not want a number like that. We're only going to deal with zeros. Whatever you put in here, it has to make something 0 and positive. All right, so what do we have? We've got one that's going to go in the other direction. Woo. And so let's call this 4, 9. Now let's go over here and call this -1, comma, oh, let's go 28. Right? So you bring that into me and show me that you have done that without having any numbers, flat numbers like this. I don't want any flat numbers. Why did I call it flat? I don't know, but I did. That's because I'm a little tired. All right, so that's the second topic that you're going to have to deal with. The third one is graphing, not graphing, but just writing the equation from a graph that is going to be exponential in nature. So let's say y equals 5. That's the dotted line. And my range is y values are greater than 5, even though they get very close to 5 on the left. And let's go over here and let's call this 1900. And let's call this 8. And let's go over here and let's call this, yeah, I guess I'll do that a little bit. I guess I'll go all the way across. Might be easier for you to understand. The asymptotic behavior is over here because these y values aren't anywhere near 5. All right, so let's go. Let's make that one there. Maybe I'll get a little better picture, and that one there. That's a little better in terms of representation. And so let's make this 1950, comma 11. All right, so the trick here is to list the 3 values for y. 5. I don't have to read this from left to right, but I think it's easier. 5, 8, and 11. So I want these 3 numbers to show up. And I think it's safe to say that all the y values on this graph are bigger than 5. That's step 1. Making sure you understand that. Then the question is, how much bigger? Well, I don't think that's a big jump in understanding. How do you get from 5 to 8? You go up 3. That's really can be shown right there. Going up 3 units from here to here. Now I've got to measure from 5 again. Right? But this number is going to get in the way, so let's get rid of it. Let's just get rid of it. That's the question. From 5 to 11. Well, that's 6. Okay, so I don't know if you start to see, but I got a doubling process here. And if I'm looking to the left, a cut in half process. If I, take more time to draw it a little better, because I think it would be coming down a little quicker than what I did there. But the bottom line is all we need is 2 points in the asymptote. And this is the hardest part. It's exponential, right? Talked about exponential growth. Hopefully that's starting to resonate with you. And what's the class based on? Zeros and ones. And what's b to the 0? 1. What's b to the 1? B. So b to the 0 means I can make the parentheses 1. And b to the 1 means I can make the parentheses b. Okay, so how do I make a 0 out of 1900? Minus 1900. And 1900 and 1950 tells me that every 50 years, I'm getting this. So 50 years from now, that's going to double, right? And so if this is 3 and this is 6, I should go up 12 units on top of 5. Let's see if that happens in the year 2000, because that's 50 more than 1950. So 2000 minus 1900 is 100. 100 divided by 50 is a 2. Well, this is the number 2. 2 squared is 4. 4 times 3, yep, a jump of 12 on top of 5. All right, so let's do another exponential growth model. And the only reason it's growth is we're reading from left to right. If we were reading from right to left, I guess I'd have to call it a decay model. There'd be a sign change there. Sign changes exponentially. Remember what a sign change exponentially does. 5 squared is 25, but 5 to the negative 2 is 1 over 25. So negatives flip the base. All right, so looking to the right, growth, looking to the left, decay. Let's try this one. Let's let y equal 3. And now I'll just do a random just some random numbers. Again, growth, if we look left to right, decay if we look right to left, but let's go here. Let's say in 1957, there were 20 of something. And way up here, let's go in 2001, there were, I don't know, 51 of something. Okay, maybe this is drawn to scale, doubtful. Okay, you pause. The new numbers for Y's are 3, 20, and 51. 3, 20, and 51. How do I get there? I start with Y equals 3 because every Y value is above 3. Plus sign works well for that. How much above 3 is 20? 17. Well, that's the first calculation. The second calculation is not up 17. The next calculation is 3 to 51, which is 48. So this is about a 3 to 1 ratio. Okay, a little more, it's a little less than 3. Yeah, a little less than tripling. Okay, and now 1957, x minus 1957, and drop a 2000 in there, and we got 43, 44, I believe. There's 44. All right, we're just concentrating on being able to work with a graph here and being able to name it. It's not rocket science. You are quite capable of getting the mechanics, and then we can talk about it for the remainder of this lesson. So we can really start to talk about how we work with these models. All right, so now we'll do a decay. Newton's law of cooling, 60 degrees in the room. I pour my coffee. After 5 minutes, my coffee registers 140 degrees. So this is a degree symbol. Let's say that in another 7 minutes, or minute 12, it registers 100 degrees. All right, so 60 degrees. How do I got to read left to right. So my 3 numbers are the asymptote, because this coffee is going to cool to 60 degrees. How do I get to 140? And then how do I get from 60 to 100? Well, those are the considerations. So 60 degrees, and I'll work with this one a little bit, plus 80 degrees, and this is years. Right, so, oh no, minutes, I forgot. Newton's law of cooling. So we're going to go from minutes to temperature in degrees. And hopefully you can see the conversions here now that I put the units of measurement with them. So 80, the next one is not 80 degrees. The next jump is 60 to 100, which is 40 degrees. And minutes 5, I'll use T this time. T minutes minus 5 minutes over a change of 7 minutes. Now let's watch what happens when we put a number like 12 in. 12 minutes minus 5 minutes. 7 minutes. 7 minutes divided by 7 minutes. Minutes goes into minutes, cancel, and 7 goes into 7 one time. So I just have a generic 1. Degrees divided by degrees cancels. 40 over 80 is a half. 1/2 to the 1 is just a number, a half. But half of 80 degrees is 40 degrees. Added 60, and I have changed from minutes to degrees. Right, that's the second one. I'll give you a third one. Let's see which one I want to give you here. Or the fourth one. I'm on the fourth one, so another decay. Let's do another decay. Let's talk about the year 2003. There were 20 sheep. No, I don't want sheep population decaying. There were 20, who knows? I don't know. And let's go to 2023. Let's make it 2033. What do we have? We've got something, some smaller Y value. Why don't we go 11? Now let's make this Y equals 5. Okay, and push the space bar. I'm just gonna do the equation quickly this time. So y equals 5, how do I get to 20? I'm going up 15, next time I'm not going up 15. I'm going from 5 to 11, which is 6. Time, t minus 2003, and elapsed time 2003 to 2033 looks like 30 years to me. That's that equation. One more, and you'll get a crack at this tomorrow. And there's another rapid fire 5 somewhere on my YouTube channel. So if you want to get more practice with it, look for it. All right, so let's go back to growth. Let's go y, let's get a negative in here, -4. Let's go with 1800 was a very good year because there were 2 of something. And then up here in 1905, another very good year because the population jumped from 2 to 17, not drawn to scale. So y equals -4. How do I get from -4 to 2? I go up 6. Next time I don't go up 6, I -4 to 17, I go up 21. You know, you don't have to reduce that fraction for me tomorrow. You could divide by 3. So why don't I do that? So 3 goes into 21/7. 3 goes into 6 twice. We get a little better feel for something that is 3.5 times bigger each time. So this should be 3.5 times that, so on and so forth, and infinitum. And now I've got a time of 1800 minus 1800, and elapsed time of 1800 to 1905, 105. And 5 practices. You can always come back to it an hour or two, give yourself a chance to forget it. Play the video again. You know, you're gonna try to get it right tomorrow. And if you come in with a blank, I know you're not looking at the videos, which is why I'm doing the daily quiz anyway, because I could tell some folks weren't looking at the videos. Just for the record. All right, I'm gonna upload this, put it on Canvas, and when you walk in the door, you got 5 minutes, and then you go onto the board working on a worksheet.